In this presentation, I am going to explain the previous GATE questions and answers for the year 2022, and the topic covered is analog electronics. Now let us see 2022 GATE question, that is first one. For an ideal MOSFET biased in saturation, the magnitude of the small signal current gain for a common drain amplifier is, the different options are A infinite, B 1, C 100 and D 0. Therefore, this is the question, that is small signal current gain is to be for a common drain amplifier. For a common drain amplifier means drain is common to input and output. For example, in this circuit we can see that one, the input is given between the gate, and actually this point is source, because when we draw the AC equivalent circuit of this one here, we can see that one, this point or this VCC can be, that DC source can be shorted, so that this point is same as the ground voltage, or can say that one, or the drain point is same as the ground voltage, or we here the input is given between the gate and of course the drain, and the output is taken between the source and drain. Or drain is common to input and output, that is why it is called a common drain amplifier. And it's also another name is called, it's a source follower, because the voltage gain of this amplifier is near to unity, meaning that source is following the input. The gain is unity, as well as the phase shift is also equal to 0. That is why here the source voltage is almost same as, or that is following as the input voltage. That is why it is called a source follower. Therefore, this is a common drain amplifier or source follower. The question is that what is the small signal current gain? Now, the small signal current gain in a common drain amplifier or source follower is defined as the source current, that is Is, divided by the gate current Ig. The ratio of the source current, that is the output current in common drain amplifier, that to the gate input current, that is gate current is Ig, or Is by Ig. Since the impedance is very large, here the impedance at the input side is very large, the input current is negligibly small, that can be approximated to 0. Since the input current is approximately 0, then the ratio of Is by Ig, that will become infinite. Therefore, the answer is the option A, that is the small signal current gain for a common drain amplifier is infinite. Now, the second problem of 2022 GATE question, that is second, the steady state output voltage V out of the circuit shown below is. This is the circuit, is op-amp circuit, in which this is a non-inverting terminal that is grounded through a resistor, or that is the V plus terminal here. V minus terminal, to that one we are applying a input voltage, constant DC voltage of 0.1 volt is applied here, and the feedback circuit, there's a capacitor is there, and output is taken here, and these are the biasing voltages, of course plus VDD and minus, it is equal to minus VE. Here this is the biasing voltage. Now the question is that what is the output voltage? That options are A saturates to minus VE, B saturates to plus VDD, that is this voltage, C becomes equal to minus 0.1 volt and becomes equal to plus 0.1 volt, that is the choice D. Now let us see the circuit. The same circuit is shown here. The input is equal to 0.1 volt, and the resistance, this is the resistance R, and this is the capacitance, and this is the resistance in series to the non-inverting terminal. Assuming the op-amp is ideal as per the virtual ground concept, the voltage at this point, or V plus, is equal to V minus. V plus equal to V minus. Therefore, since this voltage is ground voltage and this voltage is also equal to, this is also ground voltage, this V minus will become ground voltage. Now we can apply the KVL to this loop, that is this from this one, this coming to this one, and coming to this one, and coming to this one, and this output, and we can apply the Kirchhoff's voltage law to this loop. Then point, that is, and first thing that assuming the op-amp is ideal, the virtual ground concept, V plus equal to V minus, or this voltage is equal to 0 voltage. Applying KVL to this loop 1 or to this loop 0 plus, or this loop, actually here this loop is taken as the in this case applying the to loop 1, this one, and that is equal to the voltage at this point is equal to, with respect to this one, equal to 0 voltage, that is 0 plus the here the voltage that is equal to VCT, that is the drop across the capacitor, and the output voltage plus V out equal to 0, or V out equal to minus VCT. The output voltage is equal to minus VCT. They are applying the Kirchhoff's voltage law to this loop. Now continuing the same problem, and here first we apply, we have the KVL is applied to this loop and we got the corresponding equation. And the second stage, we are at this node, we are going to write the KCL equation, Kirchhoff's current law equation at this node. And at this node, this voltage is equal to 0 because this virtual ground or virtual ground short circuit of this one, this voltage is same as this voltage, or this voltage is equal to ground voltage. Now applying the KCL at the node V minus this one, and this current which is equal to 0.1 minus 0 divided by this resistance R1. That current, since the input current is, the input impedance is on resistance is infinite, ideal case, therefore this current is equal to 0. So whatever the current coming this to this node will be going through this one also. Therefore this current equal to 0.1 minus 0 divided by R1, that is equal to, which is equal to, that is 0.1, that is equal to the this current, that is the capacitor current. Capacitor current is equal to the current through the resistance, which is equal to 0.1 minus 0 divided by R1, or 0 divided by R1. As per the capacitor, as the capacitor current is constant, that is capacitor current, because we have this, as we can say that capacitor current equal to 0.1 divided by R1 is a constant. And since we are constant current is flowing through the capacitor charges increases linearly, and the due to this increase in charge, the voltage across the capacitor, or the VCT, is equal to 1 by C integral whatever this current, that is ICT dt, or 1 by C integral 0 to T ICT dt is the voltage across the capacitor, or ICT, or current through the capacitor is already, it is equal to same as the input resistance current, which is equal to 0.1 divided by R1, or 1 by C integral 0 to T 0.1 divided by R1 dt, or 0.1 divided by R1 into C integral dt on 0 to T limits, or 0.1 divided by R1 C into T. For 0.1 divided by R1 C, this is a constant, some constant into T, where we can say that one, this is a straight line equation in which this represents the slope of that straight line, 0.1 divided by R1 C into T. Therefore, if we draw the corresponding diagram of this one, that is the voltage across the capacitor with respect to the time, as per this equation, it is a straight line equation, and the slope of that straight line is equal to 0.1 divided by R1C. Therefore, this is the variation of the capacitor voltage with respect to the time. Now, from the above graph, the capacitor charged continuously up to infinite time. If you see that one, it is charged continuously up to infinite time, and the V out equal to, in that case you can say that already we have derived V output voltage is equal to minus of VCT, or minus of VCT means that it is equal to minus of 0.1 divided by R1 C into T. Therefore, the output voltage equal to, which is equal to negative of this capacitor voltage minus of VCT. Therefore, the output voltage equal to, which is equal to, it is equal to minus of 0.1 R. Therefore, minus is the capacitor voltage, which is equal to minus 0.1 R1C into T. Now, continuing the same problem, V out equal to minus VCT, which is equal to, again it is equal to V out equal to minus VCT, which is equal to minus of 0.1 divided by R1C into T, and this is having a negative slope of 0.1 R1C. That is why that is represented here. The output voltage waveform with respect to time, we are having the equation minus 0.1 divided by R1C, and the slope is equal to negative slope, which is equal to minus 0.1 divided by R1C. And the graph, this V out is shown here as time at the infinity, or after some times this one, the that gets saturated, that is getting saturated to the biasing voltage. Therefore, here under steady state condition at time t equal to infinity, V out will become, as per this one, that is equal to infinity. But op amp does not allow the output voltage to come to the minus infinity. Therefore, it saturates to a voltage. Here it saturates to a voltage of minus VEE. Or therefore, output voltage equal to minus VEE. And that is why the option is the op amp is getting saturated to minus VEE. To this voltage it gets saturated. For option answer is option A. Now let us see the third problem of 2022 gate question, that is for the circuit shown below with ideal diodes, what is the output voltage, that is the output will be, this is the input voltage and this is the circuit in which the diode D1 and D2 and the resistor is connected between that. This is the input voltage and the question is that what is the output voltage. The options are A, V out equal to input voltage V in for V in more than 0, that is during the positive half cycle. Option B is V out equal to V in for V in less than 0 for negative half cycle. Option C is V out equal to minus V in for V in more than 0, or for positive half cycle it is equal to minus V in. And V out, option D is V out equal to minus V in for V in less than 0. So these are the four options. The circuit is this one. And for the positive half cycle, that is 0 to pi radians, we can see that one. This is getting forward bias and this is also getting forward bias, or D1 and D2 are getting forward bias. Therefore, the equivalent circuit is this one. That is, they both are shorted. Here this is shorted, therefore this is the equivalent circuit corresponding to the positive half cycle of the input, that is 0 to pi radian. This is the equivalent circuit, and then output voltage will be same as the input voltage. V out equal to same as V input voltage during the positive half cycle. And for the negative half cycle, that is during pi to 2 pi radians, negative half cycle, we can see that one, both are reverse bias, because here we'll be getting a positive voltage, that is why it is reverse bias, and here also we'll be getting, this is negative voltage, this is positive voltage, that's getting reverse bias, and here for negative voltage, that's also getting reverse bias. Therefore, it is just like open circuit, both 1 or D1 and D2 are open circuited, and therefore the output voltage is equal to 0 voltage. Therefore, during negative half cycle, pi to 2 pi radian, output voltage equal to 0. Therefore, the answer is that for the negative half cycle and negative half cycle, D1 and D2 will be off and replaced by open circuit, so the circuit becomes as this one. For the negative half cycle, that's the equivalent circuit of this one is that therefore the output voltage is equal to 0. So for the negative half cycle, D1 and D2 will be off and replaced by open circuit, so the circuit becomes as shown this one. And the answer is that V out equal to V in for V in greater than 0 and V out equal to 0 for V in less than 0. V out equal to V in for less than 0. Or in this, from this option, the correct answer is option A, V out equal to V in for V in more than 0. Therefore, the option A is the correct answer. Correct answer is option A.